Bayesian learning is very important concept for machine learning. So, in this video, I will explain what is the meaning of Bayesian learning. So, to understand Bayesian learning, let's quickly review what is Bayes' rule and what is Bayes' classifier. The Bayes' rule is very simple, which is about conditional probability. So the conditional probability y equal to label k for given x is equal to probability x equal to x for given y equal to k times probability y equal to k over probability x given x. Okay, essentially the probability of a given b is equal to probability a and b for given probability b, which is equal to probability b given a times probability a over probability b. This is Bayes' rule. And for the classification task, we can write Bayes' rule in this way. So we basically have three components. This one, and this one. Each component has its own property. First, the property x equal to x, the denominator, which is independent to the model. Whatever your model is choose, the probability x equal to x never change. You always have the same probability density function for this denominator. Okay, and this part is called density function, which is denoted by fkx in our textbook, which essentially presents some density for your observation point x, for your input point x, when the true upper label is equal to k. Okay, this term is called prior knowledge or prior distribution. So why this is called prior distribution? Because this is independent to your input x. Okay, no matter which input you get, the prior distribution always the same, which is given us before we observe something. So this is called prior knowledge or prior distribution. And accordingly, this is called posterior distribution or posterior knowledge. Okay, then what is Bayes classifier? Bayes classifier essentially find the label index k star that minimize the classification error or maximize the conditional property. And from the property, the denominator of this conditional property independent to the model, your learning process, which is essentially equal to arg max property x given y equal to k times property y equal to k. Okay, so this is Bayes classifier. So let's rewrite this. The k star is equal to argmax k, the density function, times prior distribution. This is Bayes classifier. Right. Or of course we can directly use the conditional distribution, not use the density function. Property y equal to k for given x. In the previous video clip, the logistic regression essentially directly compute this conditional probability vector using score vector, logit vector, and softmax function. Okay. But we can find the k star using density function and prior distribution. One example of this approach is LDA in our textbook. LDA have important assumption. The density function fkx is a normal distribution such that 1/√2 pi sigma times exponential minus 1/2 x minus mu k over sigma square. Okay. Then once we obtain sigma mu k for every class k and pi k, we can conduct classification, right? Because we can compute the density function and we can compute the prior distribution, right? Then how can we train fkx, the density function, and the prior distribution? For the LDA process, we can estimate the prior distribution from the number of training samples, number of class K samples over number of total samples. This makes sense, right? Among all data points, how much portion of your training data point belong to class K? That will tell you the prior knowledge. Then how can we obtain mu hat k and sigma? So mu hat k is, so let's say this is nk, this is this n. Mu hat k is 1/nk times sum of x I belong to the class K. Okay, which makes sense which is just empirical average of your input X for class K. Sigma, this is also empirical variance of your observation. This n minus capital K times summation K1 to capital K summation I belong to set K xi minus mu hat K square. So this is empirical covariance of your input X. Why we have to use n minus capital K instead of just n? Because we have K mu hat K parameters. So degree of freedom we spend for fitting mu hat K is capital K. So we have to subtract capital K from the total number of samples. Okay. That's it. This is the LDA process. From this estimation, we can understand what is the density function and what is prior distribution. From the density and prior distribution, we can classify any input X. Indeed, this mu hat K, pi hat K, sigma are the best parameters that maximize log likelihood function. Under the assumption, LDA follow the normal distribution. The proof is out of scope of this class, so I will stop here. But this is true, believe me, and this is very nice approach to design some classification algorithm. And Bayesian approach is very important. So I will explain more in the later video clips.